Hey there, Nate from Microchip Technology here to talk about the AVR SD and how its features directly support safety-critical applications. Now, the AVR SD is designed in compliance with ISO 26262 and IEC 61508 up to ASIL-C and SIL-2 respectively. However, these features provide compelling benefits for any design that needs to function with a high degree of safety. So even if you aren't specifically designing for one of these two standards, there are still features to keep your next design robust and reliable. Now, in a recent video, we covered how the AVR SD's features and design specifically help achieve ASIL-C and SIL-2 compliance. And since many features were created with those standards in mind, that video provides important context for how the AVR SD supports these applications from a compliance point of view. Our focus here will instead be on the features themselves and how they make the designs safer. However, a link to the previous video will be included in the description below. With that in mind, what are some examples of the AVR SD using design redundancy? To start, one of the most exciting features intended for safety through redundancy is the dual-core lockstep CPU, or DCLS CPU for short. The AVR SD's dual-core lockstep CPU is a key feature designed to enhance functional safety through architectural redundancy. In this configuration, two identical CPU cores execute the same instructions in parallel, with their outputs continuously compared by redundant hardware comparators. If any discrepancy is detected between the core's outputs, a device reset is immediately triggered, ensuring that faults are caught in real time rather than after the fact. Even this reset has redundancy, with one path to the reset controller and the other through the error controller to float pins and request a reset. This configuration fulfills important requirements for ISO 26262, ASIL-C, and D, as well as IEC 61508, SIL-2, and SIL-3 to aid in functional safety compliance. Since the DCLS CPU is strictly lockstep, both cores must operate together and cannot be used independently. Included with these dual CPUs are dual interrupt controllers for the CPUs that support non-maskable interrupts for effectively handling faults in critical functions. The DCLS CPU also has additional safety mechanisms such as built-in opcode and illegal address detection, which further protects against erroneous or corrupted instructions. For development and validation, the DCLS CPU supports fault injection, allowing engineers to simulate faults and verify the system response. If that sounds like a lot of information all at once, don't worry, the core idea is simple. Let's take these two cores and label them Core A and Core B. When the CPU runs an instruction, for example, adding two numbers, both cores receive and execute this instruction at the same time. Then the results of both Core A and Core B are compared. If they match, then everything is normal and the device continues to the next task. If the outputs don't match for whatever reason, then the device resets. Supporting this pair of CPU cores is a collection of key core-independent peripherals that also come in pairs. These handle important tasks separately from the CPU while retaining safety-critical redundant coverage. A few examples include two ADC modules with independent voltage references to aid with verifying analog readings, or for backup if one ADC malfunctions. Two SPI communication modules and two I2C communication modules to serve as redundant backups for communication between the AVR SD and other devices. Two zero cross detects for detecting when alternating signals cross ground. And two independent watchdog timers for monitoring application timings and ensuring proper program flow. These eliminate the need for an external redundant watchdog. Furthermore, the two watchdogs are slightly different, with one standard watchdog and one synchronous watchdog. The inclusion of one synchronous and one traditional watchdog timer is advantageous since each timer is ideal for covering specific aspects of an application. The main difference between the two is that typical watchdogs run independently from the CPU, making them an ideal fit for broader windows and monitoring core-independent peripherals, while a synchronous watchdog runs on a clock periods from the CPU, making it great for monitoring software and watching for sequencing failures where a tight window of time is required for catching errors, since the standard watchdog timer's core independence can also lead to jitter due to timing variations between the peripheral and the CPU. Continuing on, the AVR SD has an extensive list of safety features for safety-critical designs. Let's take a high-level overview of what many of these features are. In this video, we have already covered the dual-core lockstep CPU with dual interrupt controllers and illegal address and opcode detection, and dual peripherals such as the ADC, I2C, and SPI modules, zero cross detect, and watchdog timers. And in a previous video, we took a deep dive into how the AVR SD fits into ISO 26262 and IEC 61508 in general, and ecosystem support, the error controller and error injection features, and ECC memory protection. These topics are all quite complicated, so instead of covering them again here, I encourage you to go back and watch the previous videos in this series if you haven't already, which leaves these remaining features. So let's cover each of these in brief. The Program and Debug Interface Disable, or PDID, prevents unauthorized changes to application code by disabling programming and debugging interfaces on finished devices. However, the device may still update using a bootloader. The On-Chip Debug Monitor, or OCD for short, is a feature inside the CPU core that continuously monitors the on-chip debug system and triggers a reset if abnormal activity is detected. The CRC scan verifies the integrity of the application code using a cyclic redundancy check memory scan to compare a calculated value based off of portions of the device flash memory to a saved value before allowing the CPU to exit reset. Program and data bus parity detects both transient and permanent faults on the data and instruction buses. To clock failure detection modules to identify clock source failures and automatically switches the system to a fallback clock to maintain operation. To clock frequency monitors that monitor the system clock frequency to detect deviation from expected values. Core supply voltage monitors continuously check the core supply voltage and flag any under or over voltage conditions. The stack monitor detects stack pointer corruption and software bugs by monitoring stack usage. This stack monitor can catch both underflow and overflow errors. The UPDI disabled monitor alerts the system if the Unified Program and Debug interface is accidentally activated, which can potentially cause faults. Accidental sleep protection prevents the system from unintentionally entering sleep mode, which could lead to faults or unexpected behavior. And redundant reset mechanisms and safe state transitions ensure the system transitions to a safe state even if a reset mechanism fails. It should be noted that many of these features and mechanisms are more detailed than we have time to describe here. So for more information on any of these features, please see the AVR SD datasheet. That concludes how the AVR SD's enhanced safety features support safety-critical applications. If you're interested in learning more about how the AVR SD supports safety-critical designs, check out our previous videos where we cover how the AVR SD supports ASIL-C and SIL-2 compliance for the ISO 26262 and IEC 61508 standards, how the AVR SD's error controller detects, manages, and tests faults, and how the AVR SD protects and preserves its memory for safety-critical applications. If you want to get started or learn more about functional safety, please check out our functional safety courses at Microchip University, our AVR SD line of microcontrollers, and the AVR SD Curiosity Nano board. If you like this content and want to see more, please don't forget to like, comment, subscribe, and ring the bell while you're at it for notifications on any future videos.